Salam Sejahtera and hello. My name is Yashinda Sanalaki and Kannada's mathematics number is AE 2028. Today I'm here to present my group's project on high voltage engineering, which titled as Polymeric Insulator Design for High Voltage Transmission Line. We are from section 3, group 10, and the fellow presenters will be presenting with me is Chin Chung Wai, Christopher Kwek Shu Lin, Ahmad Amirul Ashraf bin Uthman. And our lecturer for this section is Professor Madya IR Dr. Aisham bin Abdurrahman. Let's go. Firstly, the general summary. High voltage insulators are critical in ensuring the safe transmission of electricity from the source to the customer. They prevent flashovers by managing sudden voltage increases and protect the supporting structures of high voltage lines. Proper design and adherence to specification are crucial for high voltage insulators. Poorly designed insulators pose significant risks and must withstand challenges like lightning strikes, impulse over voltages, and harsh weather conditions. This material used in high voltage insulators must have excellent dielectric properties and be capable of withstanding high electrical stress and environmental effects. Additionally, they need sufficient tensile, compressive, and cantilever strength to support transmission loads and maintain mechanical integrity over the system's lifespan. Common materials include porcelain, toughened glass, epoxy resin, and polymer composites. Moving on to the problem statement. Glushkov in 2014 identified significant issues with traditional insulators such as pin insulators when used at high voltages, which is 132 kV. These issues stem from the substantial increase in size and weight, making them impractical to handle and replace. Additionally, traditional materials like porcelain and glass lack sufficient mechanical strength and are vulnerable to environmental stresses. Polymeric insulators are presented as a superior alternative to traditional materials for 132 kV applications. They offer improved mechanical strength and durability, effectively addressing the challenges posed by environmental stresses like UV light, temperature fluctuations, ozone, and pollutants. These studies highlight the importance of understanding the aging process of this material to ensure their longevity and reliability. The project developed a 132 kV polymeric insulator designed for optimal performance in both dry and wet conditions. The core, typically made from fiberglass reinforced resin, provides the necessary mechanical strength while the external cover extends the leakage path length and protects against weather conditions. This design ensures the insulator's effectiveness irrespective of environmental factors. Nextly, let's see the project objectives. Firstly, to design HV insulators using suitable approaches supported by formal literature, and then to sketch an insulator model for a 132 kV transmission line tower, and then to create the proposal using the 3D drawing software of Tinkercad, and to simulate the high voltage and EM field distributions on the suggested prototype using FEMM software. Lastly, to analyze the prototype's performance when stressed by environmental impact and devise a test setup for proper HV testing that considers correct equipment, safety, and practical method. Nextly, the scope of the project. Firstly, we used Tinkercad software for the conceptual design of the insulator model, and then we performed analysis on the simulation using finite element methods magnetics FEMM. Thirdly, the 132 kV suspension type for the overhead line insulator was put to the test in both wet and dry situations. Lastly, we examined the protection and practical procedure when testing the insulators. Technical summary methodology of FEA simulation. The project workflow begins with evaluating insulator characteristics and selecting appropriate polymer materials for a 132 kV overhead transmission line. This involves Tinkercad for initial 3D modeling and FEMM software for subsequent analysis, adjustments, and documentation of results. FEMM software is utilized for insulator simulations through the creation of a new electrostatic analysis project. This includes configuration of axisymmetric scenarios, creating a 2D model in millimeters, specifying material properties, setting voltage levels, and enforcing boundary conditions, followed by mesh creation and simulation execution to assess the insulator's performance. Lastly, the design process, as depicted in the flowchart and block diagram, the final representation of the polymer insulator. The final outcome represents the completed polymeric insulator, demonstrating the thoroughness and effectiveness of the design process.
Okay, next, my part is a technical summary of chosen concept design. In my part, I will explain about insulator and polymer insulator. Insulator are essential component in the power system responsible for transmitting electricity across vast distance. So they ensure overhead lines are supported and avoid contact with the structure supporting them, which guarantees the efficient and safe delivery of electricity. Uh, as we know, polymer insulator were introduced in 1960. So they have been considered a valuable substitute for ceramics one by the electric utility and equipment manufacturing process. Among the notable benefits of polymeric insulate of the polymeric insulator are their reduced weight, which allow for more streamlined line design and their capacity to prevent a series of failure. Over a 3 decade of usage, polymer insulator coated with organic silicon have shown almost no degradation from solar radiation in various climates. It's also polymer insulator exhibit high resistance to vandalism. Okay, next is the proposed 2D and 3D drawing of polymeric insulator. For our project, we propose a model of 132 kilowatt polymeric insulator. The design feature have a 9 sheets comprising 5 smaller and 4 larger ones. The radius of the smaller sheet is 100 millimeter, while the larger sheets have a radius of 110 millimeters. Each sheet is inclined at a 45 degrees angle. So the table show the overall insulator parameters and specification. As we can see, the system voltage is 132 kilovolts. Type option is long rod. Material option is polymer. Maximum length 570 millimeters. Creepage clearance 970 millimeters. Arc distance 440 kilometers. And last one, fitting option is a caps and pins. Okay, next is the process flow finite element analysis, which is FEA, simulation to the prototype. First is this is the flowchart of the projects. So it starts with the various insulator properties are analyzed to assess their respective advantage and disadvantage before any design work commence. So the following a comprehensive review of existing literature. Polymer materials were selected for the insulator designs suitable for 132 kV overhead transmission line. The design process was facilitated by employing the Tinkercad software, which allow for creating a 3D model of the insulator. The next step involved simulating the 3D model of the insulator using FEMM. So the simulation process began with assigning the necessary properties to each part of the model. If the initial simulation failed to produce a precise value and waveform, adjustments were made and the simulation was rerun. So next, the successful simulation resulted in the data and outcome that were carefully recorded for discussion in the subsequent sessions. Okay, so this is the schematic overview of block diagram of FM software workflow for simulating insulator. It starts with the new project, configuring it for an electrostatic problem. This setup involves selecting millimeters as the unit of length and specifying the problem type as asymmetric to account for the insulator asymmetric simulation condition. So this 2D model matching the prototype dimension scale to millimeters should be developed, and then the subsequent stage involves specifying the primitivity properties for each material involved and setting the operation voltage level for the conductors. Measuring open boundary conditions are applied. Completing these preliminary steps allows for proceeding to the mesh generation phase, followed by running the simulation to exact result. Analyzing the values for the high voltage and electrical field generated by the simulations is essential to validate the insulator efficiency for use in transmission lines.
Good day, sir. My name is Christopher Quack. My metric number is AE20063. So now I'll proceed with the presentation for simulation. So we are using FEMM as our simulation software. So our system voltage proposed is 132 kilovolt. We are using long rod, and the material for our insulator is polymer. The proposed maximum length is 570 millimeter. Creepage clearance is 970 millimeter. Arc distance is 440 millimeter. And the 50 options used is cap and pins. So the voltage distribution of HVAC test and also the electric field test under dry and wet test under two conditions. One is clean and another one is contaminated condition. So the design features consist of 9 shafts, so 5 smaller ones and also 4 larger ones. So the radius of the smaller shaft is 100 millimeter, while the larger shafts have a radius of 110 millimeter. So each shaft is inclined at 45-degree angle. So as you can see, this is for the simulation for the dry clean one. Okay, we are using air, steel. This is a fiberglass steel. So For dry clean and wet clean, both is in air. Okay. And for dry contaminated, we are using a cement for the contaminated condition. So basically, I will show the simulation only for one. Basically, the conditions are all the same for all simulation done. Okay, so now I'll show. So first I mesh it. Okay, okay, okay. Then okay. So after meshing, this is the 1.32 132 kilovolt. So I'll connect the lines of this. Okay. Okay, so first I'll show for the HVAC test. Okay, so voltage. Okay, so this is the plotting of the graph obtained for the HVAC test for dry clean. So basically, it's the same procedure for dry contaminated, wet clean, and also wet contaminated conditions. So this is the graph voltage potential, and this is the length in millimeter. So now I'll show for how we got the uh, electric field, how we do the electric field test. So for the electric field test, so it's the same procedure. So connect the line. Okay, so this is the electric field graph. So this for the wet clean. So this is the electric field test graph generated. So this length is in millimeter, and this is the graph shown. Okay, so I'll explain more briefly in the presentation slide later on. So now I'll present the voltage distribution of HVAC test. So this is the graph obtained from the FEMM simulation software. So HVAC dry test and also wet test, both condition clean and contaminated, clean and contaminated. So from this graph, you can see that the voltage distribution is uniformly and gradually increases from high to low. So from this, we can see that the polluted insulators, which is the contaminated condition, have lesser voltage distribution than compared to the clean condition. So from this, we can say that the T insulator result in a minor voltage distribution drop compared to a clean insulator. Maybe this might be because contamination may have a minor impact on the voltage magnitude. So along the insulator surface. So moving on onto the electric field strength distribution of HVAC test. Same, we test in clean and contaminated in both condition, and so dry and wet. So the difference is only visible during the dry and wet conditions with the graph of electric field strength along the creepage distance at the dry condition in wet and contaminated situations being higher than the graph of electric field strength along the creepage distance at wet conditions in both clean and contaminated conditions. So you can see here this is much higher than this, and this one is also much higher than this. So that's all for me. Pass it to the next presenter. Thank you.
Thank you, Chris. Good day to everyone. My name is Chin Chung Wei, AE 2044. Now I will continue the presentation by explaining the high voltage testing proposal of our group. Let's take a look at the safety precaution in this slide. First thing first, risk management is very important. High voltage testing mainly take place in the laboratory where this environment involves physical and chemical and also the electrical risks. That's why we need to have a proper risk management to manage this risk to prevent any accident happen. Secondly, we need to follow the PPE and also the dress code when conducting the experiment. For example, we must wear closed-toed shoes, long pants, and also wearing the personal protective equipment PPE such as the safety helmet, gloves, and also goggles. Furthermore, we need to follow the safety protocol in which we should be familiar with the safety precaution and also the procedure before we starting any testing. A safety form is required to fill up to make sure that all of us understand the lab safety measures. Last but not least, UTSHM High Voltage Laboratories Testing Zone is enclosed by an iron fence and features status lamps red and green to show that the status of testing equipment. Moreover, adequate spacing between the object and also the equipment are more safer. Regular inspection is recommended to check the functionality of the equipment. Now, let's take a look at the risk assessment form which we obtained from the High Voltage Laboratory UTSHM. So, for this experiment, the title is 132 kV overhead voltage transmission line polymer insulator.
Our project supervisor is Professor Madya, IR Dr. Rahisham bin Abdurrahman. The person who carrying this experiment is me, myself, Shin Chong Wei. And now, let's take a look at the method statement. So the purpose of this experiment is to test the composite of the insulator in wet, dry, and also salt condition. The equipment that are being used are the high voltage DC generator, glass insulator, earthing rod, DC wattmeter, and control panel. This figure shows our proposed polymer insulator. So for the experimental procedure, to test the dry condition, the insulator to be tested should be installed in the same way it will be used. Next, a variable power frequency voltage source is connected between the insulator's electrodes. The voltage is then slowly increased until it reaches the specific level. It is important to note that this voltage must be lower than the minimum flashover voltage, which is when the insulator's surrounding air breakdowns and becomes conductive. The insulator must be able to withstand this voltage level without a flashover for at least 1 minute. Whereas for the wet condition, rain test, the insulator being tested is installed in the same manner as it will be used in this test. A variable voltage source of power frequency is connected between the electrodes as in the previous test. Additionally, in this test, the insulator is sprayed with water at 45 angle so that the precipitation rate does not exceed 5.08 milli per minute. The voltage is then gradually increased until it reaches the desired level. The voltage is maintained at a constant level for 30 seconds to 1 minute, and the insulator is inspected for the puncture or breakdown. Before we conducting an experiment, we need to perform risk assessment. All the hazards that would be happen during the experiment has been listed in this table. Each of the hazard will have the control measure applied to eliminate or minimize the risk. For each of the hazard will be rated depending on the severity and also the likelihood. For example, the fire hazard, it will affect all the lab user. So how to solve this fire hazard or to minimize the fire hazard, we can put a smoke detector above the sample to provide audible notification or any fire. Also, a fire extinguisher is available in the laboratory. For the severity of this hazard is 3, and also the likelihood for this fire hazard is 1. This is the table record of the chemical usage within this experiment, and also this is a hazard checklist that I have mentioned before. Okay, now we end our risk assessment form review. Now, let's take a look at the testing setup for the HVAC. The procedures for the test is listed in this slide. Firstly, we need to ensure that all the electrical equipment in use can handle the overvoltage. Second, we need to employ an HVAC test transformer specifically for high voltage testing. Moreover, in this project, we need to simulate wet condition, where control nozzle is used to create a rain-like effect on the surface of the test sample. Whereas in the dry condition, the sample will expose to the 132 kV for 2 to 3 minutes. After the testing, all the results including the current and voltage are collected and analyzed from the testing equipment control panels. Furthermore, we need to examine the sample for any visible sign of corona discharge in which it is shown that the evidence of damage or any flashovers. Moving on to the next slide. In conclusion, there are several things that can be learned from the high voltage testing proposal. Firstly, conducting a risk assessment is crucial for high voltage testing because it involves potential risks such as the electrical, chemical, or any biological hazard. Secondly, before conducting any testing, we need to wear protective gear to enhance our safety, including the gloves, helmets, and closed-toe shoes. Moreover, we need to understand all the procedures and try to familiar with it, the testing methodologies for obtaining accurate analysis results. Last but not least, all the testing must be under the supervision of our lecturers or lab assistant when we are conducting high-risk experiments such as the insulator design testing under high-voltage AC, wet and dry conditions. With that, is end our presentation today. I hope you enjoyed this video. Thank you for watching.